Good morning, all. This is Deepak Mohapatra, HOD in Civil Engineering Department of Ganesh Institute of Engineering and Technology. We are discussing about the design of tension member of a steel structure. So first of all, we are know about tension members. So tension member are a structural elements that are subjected to axial tensile force only. So what is axial tensile force? So suppose this is a body and here is the axis. So the force acting axially, so that's why it is known as the axial tensile force. So that's why the whole member is known as a tension members. The form of tension members is governed to a large extent by the type of the structures of which it is a part and by the method of joining it to the adjacent member of the structures. So now come to the common shape of tension member. The common shape, different common shape are these are the different common shape of a tension members. And so on. These are the common shape that are using. Now come to the design strength of a tension member. Design strength of a tension member. The design strength of a tension members are the list of number one. One is the design strength due to the yielding of gross section. As per IS 800 2007 recommended that the design strength of due to the yielding, the symbol indicated as TDG. This is the design strength of yielding of cross section. Number two is the rupture strength of a critical section, that is symbol indicated as TDL. And number third one is the block shear, that is TDH. So as per the IS 800, the design strength of a tension member is the least of or the smaller value of this. So which one is smaller? We are calculate. First one, we know that the number one, first one case, that is TDG, that is design strength due to the yielding gross section, that is TDG. It is given by TDG is equal to AGFY divided by gamma MO as per clutch number 6.2. What is AG? This is the gross cross section of the section. Fy is the yield stress of the materials, and gamma MO is the partial safety factors for the failure in tension by yielding. As per its value is generally it is considered as 1.1. Now second case is the design strength due to the rupture of critical section, symbol indicated as TDN. TDN. So TDN is equal to, its value is 0.9 ANFU divided by gamma ml, which is also close number as per 6.3, near about page number 32. So where gamma ml is the partial safety factors, at ultimate states its gamma ml value is considered as 1.25, and AN is the net effective area of the members. AN, its value is equal to B minus NDH plus summation of PSI square divided by 4GI whole into T. So the symbol indicated is B is the width of the plate, DN is the diameter of, DH is the diameter of bolt hole, G is gauge length between the bolt hole, PSI is the staggered pitch between the line of a bolt holes, and T is the thickness of the plate. So thickness of the plate, let me consider as this is the plate, and the thickness, here is we are drawing a pictures, this is the thickness we are considering as a T, thickness of, generally we are considering as a thinner of thickness plate, and N is the number of bolt hole in the critical section, I is the subscript for the simulations. Now come to last one is the third one is the block shear, that is TDH, that is block shear. The TDN is equal to, its value is equal to 0.9, its value is equal to 0.9 ANCFU divided by gamma ml plus beta AGO FY divided by gamma ml. So this first one is the design strength by yielding, next one is the rupture of critical section and block shear. The design strength of tension member final value is the smallest value or the smaller value or least value of this three. Least value of the three. Now come to, we are discuss about the block shear value. So how to calculate the block shear? Third one. That is symbol indicate TdB. Symbol is equal to TdB. So as per the IS 800, suppose a plate, here is a plate. Another plate is connected, it's a tensile force is there, is connected by bolted connection number 1, 2, 3, 4. Another diagram is this way. One, this is the another diagram. The bolt, the two plates are connected in this pattern. 1 2 3 4. So here in first case, as per IS 800 recommended the following block shear value: TDB is equal to AVG FY divided by root 3 gamma MO plus 0.9 ATL FU divided by gamma ML, or TDB is equal to 0.9 AVN FU divided by root 3 gamma ml plus ATG FY divided by gamma MO. So the block shear value, the least of these two one, least of these two value one. So what is AVG and AVN? What is AVG? AVG and AVL. This is the minimum gross and net area in shear. In the first figure, let me figure A, here is the figure B. In figure A, the minimum gross and net area in a shear, that is in the line 1 2 3 4, and ATN, TG and ATN are the minimum gross and net area in tension. In the line of, in figure, let me in B, in that is in B, that is figure B, that is the direction in 2 to 3. This is the 2 3 direction. In first case, that is 1 2 and 3 4. This is the line of actions. In case of welded connection, these are all in bolted connection. In case of welded connection, the block shear of the strength TDB for welded and connection shall be calculated by taking the appropriate section in the member around the end weld. We are considering this. Now, suppose we are going to considering a problem. Let me one solving as per this the fundamental data of a tension member. We are considering a problem. Let me that problem we are discussing, and then if possible we are completing this. And so that is determine a question. Determine the design tensile strength of a plate 130 mm into 12 mm with the holes of 16 mm diameter bolt hole as per the figure. Here is the figure we are drawing here. Let me the figure that we are solving this. This is a plate and the tensile force is there. So as per figure is given, there are 4 numbers in the figure. The plate width is given. The plate width given is 130 mm, and the thickness here is the, let me we are considering as the thickness, that is how much it is, 12 mm. So 4 numbers of bolts, that is the 1 2 3 4 in this fashion. The figure is given the pitch and cross distance and distance, that is 35, it is 60 and it is 35. Whole is given, very simple problem is there. And here is we are considering as a critical section. This is a critical section also known as. We are solving, this is a very simple problem. We are determining the design's tensile strength, design tensile strength, so that value we are calculating by the strength of the plate. The list of, as you know, we are discussing here where the yielding of gross section, second one is the rupture of critical section, and the block shear strength. We are first three value we are calculating, then the least one is our the actual value. Very simple problem, and the next next class we are discussing the next part, that is problematic part and the design parts. So, thank you.